Okay, so when we're developing embedded systems, we typically need to, we need to install compiler and other toolings. The manufacturers typically have their own set of compilers. For each of their microprocessor. So, what we are gonna do is we're gonna program against the AVR at Mega 328P, this microcontroller, and it's a microchip. It was Atmel, a company called Atmel, or who created the AVR, but they got the company got Microchip bought them. But anyway, so as you can see, we have compilers for AVR MCUs. And the reason why we have been using GCC so far is, it is a good compiler and it's used a lot. But nowadays, there is Clang, there is, we also use the, for pure Windows programming, we use the Microsoft compiler, of course, a lot. But GCC, the thing is, as you will see now, we will use makefiles and we will use a special version of GCC. So what Microchip Atmel did and Microchip now owns is a special tool set, tool chain, they say, and they have a special version of the GCC compiler, and they call it avr-gcc. The reason for that is, on a microcontroller, it's not possible to run. It's not. First of all, the compiler need to be able to generate machine code specific for the microcontroller, not your PC. Other than that, it's also a crippled version of C and C++, especially C++, as you will see. It's not at all a full implementation of C++. I think the G++ version is based on C++ 11. I might be wrong, it might be 14. Actually, I don't. But anyway, it's not a full implementation, of course, of C++ 11 even. It's a lot of things like the STL and so on. It doesn't work, and it makes sense. It can't work. We shouldn't make it work, like vectors and maps and heap allocation in general. It shouldn't work. We shouldn't use it in embedded systems. So they haven't even tried to implement vectors and so on. It's no meaning to try to implement vector when you have 2048 bytes of RAM. So anyway, what we're gonna do, the easiest way to install these toolings is actually, you could, when you install the Arduino IDE, you do get the tooling, but otherwise, which I'm going to show you, is if you use this link. So the link is, this is the link, and you end up at a guy called Zach. He is really, what should I say? We are really very thankful in the embedded community for Zach, at least in the AVR community. He's created a lot of good things. He has created it's called Millis, so it's a timing library, which We might have a look at that, I'm not sure. But anyway, he is also creating builds. So the thing is, it's possible to download and build these tools directly from AVR. Sorry, Microchip, of course. But it's a pain, and I mean when this is yeah. It's not that that fun to do. So he has created. We are able to download zip files. I will only show you for Windows. If you are using Linux, I think you know most things around how to download and install and everything. So it's possible. Windows now. Okay, so download that and unzip it, and you will get, I mean, you will have a folder like this. So this is what I have fetched before. You can see, yeah, inside that folder we have avr, include, bin, lib, char, libexec. Sorry. Oh, what did I do now? Oh, sorry. Okay. Anyway, so these folders, you should copy. You don't have to copy it. You're fine now, actually. All you need to do is when we compile in the makefile, we will direct the make script to use the compiler, which is inside here inside avr bin. There is a sorry, it's not there. It's in where is it? Is it in bin? Yeah, here it is. So you can see we have avr-gcc and so on. Anyway, so you actually don't have to do anything more. What I did, since I do quite a lot of programming, I mean it's a pretty long path to get to this one. So I actually just copied into, so I have C, AVR, and yeah. So I put mine directly in the root, at least on this machine I did. But remember that the makefile I give you will, I mean, you will need to, I will try to tell you that when we get there, but you will need to direct it to the your installation, or should, installation, this isn't really an installation, we're just unzipping a file, but anyway, where that avr -gcc is placed wherever on your hard disk. Anyway, that's part one. So what we have done now, we have downloaded the toolset, because we are not gonna use the Arduino IDE. Actually, to be honest, the Arduino IDE uses some, if not more, all of the tools we are gonna use. But the thing about the Arduino IDE, it's not a good IDE at all, and it also comes with a lot of, I mean, the libraries, the libraries we use by default inside the Arduino IDE are really slow, to be honest. I mean, there are a lot of security checks and so on. So I mean, just setting a pin to 1 or 0 is 25 times slower with Arduino calls, that is digitalWrite. What we're gonna do, we're gonna do bit manipulation and modify the bit directly. So it's I mean this times, this really does matter. It does. When we are talking about embedded programming. So I mean, if we waste 25 times the CPU cycles, it will be, I mean, the battery or the energy supply will last a lot shorter. So it does matter. So I mean, we never do we never use it. And also, as I said before, so it's slow. It's a lot of unnecessary code. I wouldn't say unnecessary. It's good. I mean, the Arduino IDE is good for, you know, beginners and when learning, because all these extra things. Why is it 25 times slower? Because they are doing a lot of error checks, and you know, so we're not blowing our hardware up. Really, because it could happen when we're using when we're talking about hardware. So there are a lot of error checks and so on to keep your device safe, and that's a good thing. But it's not a good thing in production environment. Number two is licensing. The licensing of most Arduino IDE libraries, because we will use a lot of libraries. I mean, we will later on. I mean, we will code and interface against different, you know, input like buttons, output like LCD display, or you know, different sensors, temperature sensors, or whatever it is. We will typically, I mean, when we use the Arduino IDE, we have that for free. We just click, click, click. I want to use this and this and this. But if we don't look at the licensing, most of the licensing are GPL, and that's not possible to use in most commercial projects and companies. So that's also a problem. Anyway, most it's about I mean, we typically need to have control of all our code ourselves. Let's go on. So now let's create the Wokwi project, because we will simulate. And we will simulate this. So we have a button, and I'm thinking we will at first we will just and we will just make the LED so it's on. Then we will check the button, and if we press the button, then we will light the LED, or otherwise it will be off. But that's part two, and we will do it in VS Code, as I said. So we will not write any code here, because the code here, this is Arduino IDE, so to speak. This is the Arduino libraries, and we will not use that. Okay, so let's jump into VS Code then. Where is it? Yeah, actually, let's do this. Okay, as I said, I do most my embedded programming in C, because the C++ implementation, you can't rely on it as you can on C. I mean, when you start using different different microcontrollers from different manufacturers, you can almost be sure that C at least works kind of the same. C++, it's kind of okay. I mean, it's too hard for them to implement C++. They can't and they shouldn't. So it's kind of a crippled version, while C is more okay. I know, and I also have more control over C code. I mean, a lot of things. I mean, the beauty of C++ is the abstraction level you get when, I mean, when you're using classes and you're using vectors and everything. But there is a risk when using too much, too many abstractions. There's a risk of not knowing what happens inside. And when we are programming embedded, we typically won't need to know down to the lowest level what's going on. Okay, let's have a look at this one. So this is an example project, and actually it was maybe not the best one. Yeah, it's okay. I will. This is the C version of this one. Sorry, what is it? This is the C version. I will create a branch, and we will do the modifications, and then you will get, I mean, a C++ version. Although it won't be much C++ in this. I will do another video, more C++, more C++-ish code. This will I don't think it will be any C++ at all, but that's the next step. So therefore, actually, let's not do this. I could as well do. Okay, I will create a new one. I will, yeah. Okay, so I will create a new project then. And I will call, so we create a folder as usual. So there is no difference. Everything is, I mean, this is just also a folder, and we call it C++ link. All right. And the first thing is we will try to write code to make that LED blink. So we will have main.cpp. Sorry. And we will have a makefile. So the makefile, let's start with that one. And as always, you just copy and paste. So let's have a look at this one. As I said, this is the makefile for the C version, and actually there is not much to do to make it a C++ version. As you can see, okay, so we are using the GCC. Should we be using the G++? Yeah, we could, but as soon as we modify the sources to be CPP, actually the GCC is so smart. So if it finds a CPP file, it will by default use the G++ version. Anyway, let's modify it to use the G++, and as you can see, we have just one source. Let me see. Oh, we have a few other places. You won't have to modify these. That's my problem. I have been stupid when I created this, but that's another issue. Let's see. I think that's everything we need. Okay. Anyway, so this makefile is a little bit more advanced. As you can see, we have a lot of other targets. So we are, for example, we could use the makefile to upload the firmware by using the ISP target. And you can see there are a lot of extra, I mean, now, as you can see, if you install it, unzipped the GCC, avr-gcc in another folder, this is where you modify it. I think I have, no, it's okay, yeah. Okay, so you should have to modify, I think, all of these. As you can see, there are a lot of other tools as well, because when we compile, we also need when after the linking, we need to modify the exe file, so to speak, to what's called an hex file, Intel hex file, and that's the format for the microcontroller at Mega. Here's at Mega. Here we are defining the megahertz for the CPU. This is important because there is no clock, so to speak. There are only ticks. And we need to know how many ticks are there in a second to be able to measure time. So we need to know compile time, how fast, at what frequency is the clock ticking. Okay, so and it will create the hex file. Okay, so let's dive into the code. The code then, I will start by just copy pasting. Okay, so the code then, and the first time you use this, there will probably be a lot of red squigglies, and after a while, it will. I think after the first, you need to build it through a makefile the first time. Sometimes you need to restart Visual Studio Code for it to understand where are all the include files and so on. I want to remove these ones, and yeah, this is the link, that's correct. And I will also, we're not gonna use interrupts and so on. We are gonna use the LED. Let me just do this. And we are, okay, so that's the, yeah, I just, for now. Okay, so let's write some code then. As you can see, we have a LED, and it's placed on pin 2. Is it on pin 2? That's weird. Because to me, it looks like it's on pin 10. And actually, if we were to write code in Arduino, we would say digitalWrite or pin mode 10. But the thing is, that's one of the things that the Arduino does to on those 25 extra cycles. I mean, they have made it easier for us so we could use, the numbers that are printed here. But actually, the thing is, this is 1 byte, 8 bits. And this is another byte at 8 bits. Actually, byte, yeah, we call it register. So there are certain memory addresses that are hardwired or mapped to the hardware. So when we on a special address, if we modify that value, it will not modify the RAM, but it will be hardwired to these pins. So if we set the value of the variable, the magic variable, it seems, I will talk about it in a minute, the magic variable if we set it to 255, all of these will be on. If we set it to 8, then this one will be on. 1, 2, 4, 8. Yeah, this one. And the other ones will be off. So there are magic variables, so to speak, and those are called. And we don't see that when we're using the Arduino IDE and the Arduino code. So there are 3 registers. First of all, there are 3 ports. So this is, let me see, I never learned. Okay, so this is called the B port, and this is called the D port, and this is called the C port. Anyway, so okay, so I mean you will get these codes when I'm done. So there are, as you can see, there are 3 ports, and what we do then is, first, as you can see, we are setting the LED pin number 2 on the B port, DDRB, the last one. So if we use DDRD, then we will set the LED pin for the D port. And the D port is this one. Then this one will, so you can see number 2 is on multiple places, so to speak, because because we are, I mean, this port has 8 bits, this port has almost 8 bits, and this port has, as you can see, not 8 bits but 6, but that doesn't matter. So that's the thing. So we have kind of two factors to specify which pin we mean. So it's not just a number, it's first the port and then the number inside the port. Anyway, so we have actually, I will have a look at this one. It's, sorry, no? Okay. Yeah, because it's squiggless. After I have compiled it, I think it's possible to jump into the. It's pretty cool. What this is, we can see it now. Actually, we could maybe see it in my other project, which is don't have the squigglies because I have compiled it. Anyway, as you can see, this is pretty cool. Okay, so you can't see it. Let's say port B. Port B. So let's jump into this and have a look. And it's actually it's okay. So they have done it in so many steps, but it's only a pointer to a certain address. So we modify we set the pointer to a special address. Anyway, so we can modify a special address and that address is then hardwired to the pins, the port, the physical hardware. All right, let's continue. So what we're doing, as I said before, for each of the pins we need to say, should we read or should we write? Because, as you might guess, let me go back to, okay. So I mean, there could be things that we read, there could be things that we write, there could also be things that are both read and write at the same time, so to speak. But it is only one communication channel, as you can see. We only have one channel, one pin, which can only be on and off. So we need to, for each, we need to tell it, are we writing or are we reading? So it won't be, yeah, so it's possible to do both read and write. So right now we're saying that we are setting okay, so we have a lot of macros. You don't have to think about this at all. This is bit manipulation macros. We'll see if I might go into this a little bit, but basically what we're doing is we are setting a specific bit. So we are setting a specific bit on this register, and when setting this specific bit in this register, it will mean that this pin is set in output mode. Anyway, and if it's cleared, it's in input mode. I will show you that in the next video. Anyway, so okay, let's do this the easiest way we could, and that is let's okay. Let's start by setting it. Great. So we're setting port B. And as you can see, this is not the same. This is data direction register B. This is port B. So with port B, we are really modifying so we are setting this to 1. So now there is a current. And then we will sleep for, let's say, a second. So there is a function called delay_ms, and it's inside this util/delay.h. And there is no real delays, or I mean, you can't set an microcontroller in to do something else. So it's just a spin. Anyway, and then we could clear it, and then we sleep again. So this is it. I hope this will work. So we have a special pin on a special port because the pins are grouped together in, you know, a byte, like 8 bits, and they have a special name, and there are 2 registers that we already have started to talk about. That's a data direction register, and that's the port register. Anyway, which sets the value. Yeah. And this is actually all we need to do. Now let's have a look at how can we run this. If we were to use let me show you. No, it's not there. Oh, okay. If we had a real device, we could, I mean, there are some targets in the makefile to burn it, to burn the firmware to the device and so on. Now I will only you can even run it, but it actually what I typically do is, let me see. Oh, I'm not used to this. You know, actually I always use the terminal to make, but let's see what happens. I will try to just compile it as with this one. Build the current build clean. Sorry. Okay, I'm just gonna build this and see what happens. I mean, it will be weird. I think it will try to start something. Yeah, let's just ignore that. Okay, I will show you the terminal way how I do it. Anyway, let's have a look at the files. As you can see, it did a lot of things. So it ran avr-gcc, and it, okay, so I had a, okay, yeah, that's That's crazy. Anyway, okay. Never mind. I didn't even see it. Okay. Doesn't matter either. Okay, so and when we have compiled it, it creates an L file, and the L file is there are a lot of steps. So we use these ob copies to create a hex file, and the hex file then could be the hex file is the machine code, the executable. All right. So if we want to run this, then we do this. I will reveal in File Explorer. So this is where my code is, where my hex file is. So let's go to this one, the Wokwi. And as you can see, I mean, our job is obviously we need to write code, but we also need to make sure that we are, I mean, coding against the correct pins. Anyway, let's if you place your cursor on the in the editor, or what we should call it, and you press F1, you get the menu, and then you enter update. Sorry, you don't. You do upload firmware and start simulation. So when we select this, we then go to the folder, and we select the hex file. Oh, have a look at that. It's blinking, and it did work. So, and as you can see, this is, oh, but it was a lot easier to just write the code here. Yes, it is. But I mean, this is how we do embedded programming. It is not possible. I mean, we are coding on our computer, and when we want to try it, we need to transfer and run it on another device. We can't try it on our computer. So I mean, we always need to do this when we are coding and we are maybe using a real device. We typically upload by using this this thing here, this target in the makefile. I will show you that as well, I think. The thing is, for this to work, all right. So you need a terminal, and I mean, this is no problem if you're using the real Visual Studio, or you're using you know, another notepad or whatever. I mean, you don't have to. I mean, it's always possible to make using a makefile by just jumping out to a terminal. So now we have the terminal in here, but I mean, we could as well be using a terminal like this. Oh, sorry, CD. Anyway, so what we typically do is we run, no, we don't run make, we run, oh, that's the problem, mingv32.make, -make, I think. Okay, so it's already, yeah, we already, let me remove the hex file. Okay, so to run these things, I mean, it's the make file. You could of course install the regular make and have it work. Maybe if you use the Windows, sorry, the Visual Studio developer prompt, I think it will work with a regular make, but we have this mingv32-make, which is installed in, I mean, when we install the regular GCC, that's so weird. So we used we used the regular GCC inside the min.gv to compile using another avr-gcc compiler. It's kind of weird, but anyway, as you can see, it's always possible to use the command line file to build, or I mean, as I do know, some of you want to use Visual Studio. Anyway, that's all for now. In the next video, as you can see, this is, I mean, this is not C++. No, not yet, but we will do it a little more C++-ish, can you say that, in the next video.